Hello, what I want to talk about today is reductive amination. There have been some questions about reductive amination, how it relates to imine and enamine formation, how to use it in problems, and so I figured it'd be useful to have a video so that you could study it a little bit more on your own. So what I have up here is just an overview of some reductive amination key points. It's an aldehyde or a ketone plus an amine with acid and sodium cyanoborohydride. And that will give us a new amine, an amine that has an additional carbon group on the nitrogen, right? It's a very important method for amine synthesis, commonly used in industry. It's one of the top 3 reactions that pharmaceutical chemists use since they make many carbon-nitrogen bonds. It's an application of the addition-elimination of water mechanism that we've used to make amines and enamines. That's the first part of the synthesis, and then the final step is a reduction, so that instead of an enamine or imine, we get an amine. Sodium cyanoborohydride is a very important reagent. It's a selective reagent. It does not react with ketones or aldehydes. It only reacts with the aminium-ion intermediate that we form in these mechanisms, and we'll see that in just a minute. All right, and it's very important to recognize this is a source of hydride, but it's less reactive than sodium borohydride. Right, and it works well with ammonia, primary amines, and secondary amines. So any of those sources of nitrogen will work in this reaction. Tertiary amines do not work. Right? So it's only ammonia, primary amines, secondary amines. So let's start by doing a reaction with ammonia to make sure we're clear on the entire mechanism. Then we'll do an overview, and then we'll do a synthesis problem. So thinking about the mechanism, as always, when we have acid and a carbonyl, we're going to protonate the carbonyl first to activate it. Right, so that generates our more reactive electrophile. Then we can add our nucleophile ammonia. Right, that generates our tetrahedral intermediate. We can do a proton transfer from oxygen to nitrogen. Right, now we can form the aminium-ion intermediate and have water leave. Again, we said this is an addition-elimination of water mechanism, and this is the spot where we eliminate water. Right, and we've just generated our key aminium-ion intermediate, right? And this is the key intermediate that we form in all of these reactions. Right, and if sodium cyanoborohydride was not present, then we could think about that intermediate going on to an imine or an enamine. But with sodium cyanoborohydride present, this is where the hydride can add to the aminium ion, and that gives us our amine product. Right? So that's the mechanism for reductive amination. Right? We do our addition elimination of water, end of it the aminium ion, and then hydride adds. Right? So we've shown that if we have ammonia, we can generate a primary amine. Right? If we do the same reaction starting with a primary amine, we're going to generate an aminium-ion intermediate. Again, we're not going to isolate that. Then sodium cyanoborohydride will add to that aminium ion. And generate a secondary amine. All right, and if we do the reaction starting with a secondary amine, we'll again generate an aminium-ion intermediate. Which will be reduced. generating a tertiary amine, right? So the really nice thing about this reaction is depending on what you use for your amine starting material, you can get different amine products, all right? Again, we've got a primary amine, secondary amine, tertiary amine, okay? So let's do a synthesis problem just to see the application of this. All right, so the synthesis problem that I want to do is the one from exam number 2. Right, on exam number 2, this was our substrate, and the goal here was to make from 5 carbons or fewer, right? So it was synthesis from 5 carbons or fewer, right? And when you looked at this, I hope that you first said, all right, we have a tertiary amine, right? And there are several ways we know to make amines, but the most effective, as we've just been talking about, is reductive amination. So I hope that you thought about reductive amination. And if you thought about reductive amination, you would say, I'm going to need a ketone or an aldehyde plus a secondary amine, right? And then thinking about the substrate that we have, hopefully you quickly recognize that that ring has 5 carbons. So we can start with that ring, which is going to help us a lot when we do this reaction. So what we're going to do is disconnect in that position, right? And when we do that, it's going to be that aldehyde plus a secondary amine, right? That's critical for us as we think about this synthesis, right? Because if we combine those two things, it will be the mechanism that we just drew out for reaction of a secondary amine with a ketone or aldehyde to give us a tertiary amine. That's 5 carbons, so we're set with that. Then the question is, how do we make an aldehyde, right? Hopefully it's clear that we're going to make an aldehyde from a primary alcohol, right? That's how we make aldehydes, right? And when we get to that primary alcohol, again, hopefully we recognize that this ring is 5 carbons, so we can disconnect in that position. And when we think about that disconnection, this is perfectly set up for a Grignard reaction with an epoxide, right? And so that was the retrosynthetic analysis for this problem, okay? So doing the synthesis out, what does it look like? Start with the 5 carbon Grignard, react that with ethylene oxide, acid quench. That gives you the primary alcohol, PCC, yields the aldehyde, and then reductive amination. So we're going to use HCl, secondary amine, sodium cyanoborohydride, and that's going to give us our target tertiary amine. Right? So again, reductive amination, a very important, very useful reaction, an application of our addition elimination of water reaction, and using sodium cyanoborohydride to give us the final amine product.